Hi Prof, today I'm here to present our project on toxic comment classification. This project explores how we can develop an effective approach to detect toxicity in online conversations while balancing safety and freedom of expression. Here's an overview of today's presentation. We'll begin with the project background, followed by analysis of our dataset. Also, we have methodology comparison, experimental process, problems and challenges, future improvements, and conclusions. Let's go with the background first. Nowadays, balancing safety and free expression is a major challenge in online discussions. There are 72% of users self-censor due to fear of attacks, and 34% of normal discussions are wrongly flagged as toxic. What's the worst? 89% of platforms use rigid all or nothing filtering, either over moderating or letting toxicity spread. This creates a false dilemma. Excessive deletion stifles healthy discussions, while misjudgments allows harassment to persist. As a result, user trust declines, reducing platform engagement. To solve this, we need a more intelligent, context-aware detection system, one that distinguishes harmful speech from constructive debate, ensuring both safety and open conversations. Our project redefines this approach by liberating a dataset of over 160,000 labeled Wikipedia discussions, moving beyond binary classification to a more nuanced multi-label system. Traditional methods have problems such as lack of context, semantic ambiguity, and single-dimensional classification, which leads to misjudgment. For example, "Are you crazy?" may be a joke or an attack, but traditional models find it difficult to distinguish. To address these issues, our model introduces multi-label classification, which has the following key capabilities. The first one is fine-grained detection. It can independently identify 6 types of harmful content to avoid misjudgment caused by a single judgment. Secondly, the platform customizability. The platform can adjust the sensitivity according to needs, reduce false positives, and improve usability. The last one is context awareness. It can combine conversation history and context to analyze text intent and reduce misjudgments. We use the Kaggle toxic comment dataset, which contains labeled toxic comments from Wikipedia discussions. The link is followed. Next, we do some data analysis. The first step, we calculated the toxicity label correlation, and we observed that some types of toxic content are strongly correlated. For example, obscene and insult have a high correlation of 0.74, meaning that they often appear together in toxic comments. On the other hand, threat is relatively independent. This suggests that threats are often distinct from other forms of toxicity. Next, we analyze the label distribution. As we can see from the bar chart, the dataset is highly imbalanced, with some toxicity categories appearing much more frequently than others. This imbalance can affect model performance, leading to low F1 scores for less frequent categories. Also, we did the text length analysis. We can see that the comment length varies significantly, with many short comments and a few extremely long ones. This variation increases the complexity of classification, as different lengths may require different handling strategies. Let's talk more about the text length. From this visualization, we can see that comment length alone is not a reliable indicator of toxicity. Some long comments are toxic, but many are not. This suggests that instead of relying solely on long-spaced features, we should focus more on content and semantic features when building models. After the data analysis, we started to develop our models and did some methodology comparison. First, we used the traditional methods, including the TF-IDF plus logistic regression, which converts text into word importance scores and classifies comments. Also, we have count vectorizer plus naive Bayes, which represents text numerically and applies probabilistic classification. These models are efficient and interpretable, but they struggle with complex linguistic structures. To better capture the context and the meaning in toxic comments, we explore deep learning methods. On the left, we have word embeddings plus LSTM. This approach uses word embeddings to represent text numerically and employs LSTM networks to capture sequential dependencies in the data. On the right, we have word embeddings plus BiLSTM. BiLSTM extends LSTM by processing text in both forward and backward directions, allowing the model to understand context more effectively. Let's take it a step further with attention BiLSTM. This model adds an attention mechanism to BiLSTM, allowing it to focus on the most important parts of the text during classification. Instead of treating all words equally, the model assigns higher importance to words that contribute more to the classification decision. By integrating attention, we enhance the effectiveness of BiLSTM, making it more powerful in text classification, sentiment analysis, and toxicity detection. Finally, we go to the model results. This slide presents the evaluation metrics of different models used in our toxic comment classification task. To evaluate the model performance, we use accuracy to measure the correct predictions, F1 score, which balances precision and recall, essential for multi-label classification. Precision and recall to measure the model's ability to identify toxic comments correctly. Among the traditional models, TF-IDF plus logistic regression, F1 score is lower, especially for severe toxic, threat, and identity hit. The count vectorizer plus naive Bayes model shows some improvement in F1 score for severe toxicity, but still struggles with threat and identity hit, indicating that these models fail to capture the rare toxic categories effectively. Deep learning methods show a significant boost in performance. Word embeddings plus LSTM improves the F1 score for toxic comment and obscene content, but still struggle with severe toxicity and threats. Moving to BiLSTM, we observe a further improvement in the F1 score for toxic and obscene categories, demonstrating its ability to capture contextual information better. However, threat detection remains at 0, showing that the models still have difficulty recognizing certain toxicity types. Finally, the attention BiLSTM model aims to enhance performance by focusing on the most relevant parts of the input text. While it maintains strong performance on toxic, which is 0.783, and obscene, which is 0.745 comments, its F1 score for severe toxicity, threat, and identity hate remain at 0, suggesting that the dataset imbalance still affects deep learning models. Overall, deep learning significantly improves text classification performance, especially for common toxicity categories like toxic and obscene content. However, rare toxic categories such as identity hate and threat remain challenging, highlighting the need for further data balancing or model fine-tuning. Also, we made a histogram to better visualize and compare the results. Since all models show great accuracy, Although the traditional methods perform well in precision, the F1 score are low, indicating that they are weak in complex text classification tasks. Deep learning methods perform better in F1 score and recall, indicating that they can better learn the characteristics of harmful comments. Attention by LSTM does not lead significantly in all indicators, which may be due to class imbalance or the model fails to capture the characteristics of some categories well. By analyzing the strengths and weaknesses of these models, we find that traditional methods are efficient, easy to understand and interpret, and therefore a viable operation in resource-constrained environments. However, they cannot effectively capture complex patterns and semantic dependencies in text, especially when dealing with long text or content with strong contextual associations. Deep learning methods are able to identify more complex language features, capture subtle differences in text, and perform better on multi-class classification tasks.
Now, I will explore the key challenges in toxicity classification. Specifically, we will focus on three main areas: minority class prediction, resource limitations, and model complexity. These challenges are interconnected and require careful consideration to build robust and efficient systems for detecting toxic content. The first is to deal with minority class. We often deal with imbalanced data size where a kind of toxic comments are significantly outnumbered. This imbalance is a classic problem in machine learning, where models tend to be biased towards the majority class. In the context of toxicity detection, this means that models may struggle to accurately identify toxic comments because they are rare in the training data. The second problem is a high false negative rate. In toxicity classification, a false negative occurs when a model fails to detect a toxic comment, allowing harmful content to go unnoticed. From an NLP perspective, this is particularly problematic because toxic comments often contain subtle linguistic cues, which are harder for models to learn when the minority class is underrepresented. Techniques like oversampling the minority class or using advanced loss functions can help solve this issue by giving more weight to the minority class during training. Beyond data imbalance, resource limitations are another major problem in building effective toxicity classification systems. These limitations can be divided into two key areas: computational constraints and data collection challenges. Both of these are common in NLP, where large-scale data sets and complex models are often required to achieve good performance. Training deep learning models for NLP tasks often requires significant computational resources. For example, transformed-based models like BERT or GDP, which are commonly used for text classification, demand high memory and processing power. This can be a barrier for organizations with limited access to GPUs or cloud resources. Additionally, hyperparameter tuning, essential for optimizing model performance, can further increase computational costs. The last challenge is data collection. In NLP, high-quality labeled data sets are crucial for training effective models. However, collecting toxic comments is particularly difficult due to their rarity and the subjective nature of toxicity. Maybe what one considers toxic, another may not. This introduces noise into the dataset, making it harder for models to learn consistent patterns. The next is about complexity. In toxicity classification, deeper models can potentially learn from detailed representations of text. However, this comes at the cost of increased computational complexity. For example, a model with many layers may perform well on a validation side, but could be too slow for real-time deployment. Real-time applications, such as live content moderation, require models to make predictions quickly and accurately. This is a significant challenge in NLP. where models often need to process large volumes of text quickly. To achieve this, we can employ techniques like quantization, which reduces the precision of model weights to speed up inference. We have discussed the challenges in toxicity classification. Let's explore potential future improvements. These improvements can be broadly categorized into three areas: data augmentation, sampling strategies, and model optimization. By addressing these areas, we can enhance the performance and the robustness of toxicity detection systems. So data augmentation is a powerful technique in NLP for increasing the diversity and the size of training datasets, especially when dealing with imbalanced classes. One effective method is synthetic data generation, where we artificially create new samples that are mimic the characteristics of the minority class. This helps the model learn more generalized patterns and reduces overfitting to the majority class. Beyond back translation, there are other data augmentation techniques that can enrich the dataset. For instance, synonym replacement involves swapping words with their synonyms to create new samples, where random insertion adds random but contextually relevant words to the text. These methods introduce variability into the dataset, making the model more robust to different linguistic expressions of toxicity. Another key area for improvement is sampling strategies, which aim to address class imbalance in the dataset. One common approach is balanced dataset creation, where we either oversample the minority class or undersample the majority class. Oversampling techniques like smooth generates synthetic samples for the minority class, where undersampling reduces the number of majority class samples. Both methods help create a more balanced dataset, enabling the model to learn from all classes more effectively. In addition to oversampling and undersampling, stratified sampling is another valuable strategy. This technique ensures that each class is proportionally represented in the training, validation, and test sets. By maintaining the class distribution across fields, we prevent scenarios where the model performs well on the majority class but poorly on the minority class. Stratified sampling is particularly important in toxicity classification, where the goal is to achieve balanced performance across all classes. Model optimization is crucial for improving the performance and efficiency of toxicity classification systems. One key aspect is hyperparameter tuning, where we adjust the parameters like learning rate, bench size, and the number of layers to find the optimal configuration. This process can significantly enhance model performance and reduce overfitting. Additionally, regularization techniques like L1 and L2 can be incorporated to penalize overly complex models, ensuring they generalized well to unseen data. Finally, leveraging advanced models can significantly improve toxicity classification. One approach is ensemble learning, where predictions from multiple models are combined to enhance overall performance. Additionally, transform-based architectures like BERT and DistillBERT have revolutionized NLP by capturing context and semantic meaning in text. These models are particularly effective for toxicity classification, as they can understand the subtle linguistic cues and contextual dependencies. Finally, let's make some conclusions and what we can do in the future. From this project, we found two key findings: effective multi-label classification, performance of deep learning models, and the challenges of data imbalance. We also have some applications like enhanced comment moderation and early detection of toxicity. Also, we have some future research directions, including advanced deep learning techniques, handling data imbalance, and real-time toxicity detections. And that's all for our presentation. Thanks for your listening.